Hi guys, so today we're going to have a look at the acid dissociation constant, otherwise known as Ka. We're going to have a look at what weak acids are, what Ka is, how to write an expression for Ka, how we can use Ka values to work out the pH of weak acids, and we're going to have a slight introduction to something known as pKa. So let's get straight into it. So first of all, weak acids. Weak acids partially dissociate in aqueous solution. Therefore, an equilibrium is formed. So in my example right here, I have ethanoic acid, which partially dissociates into ethanoate ions and hydrogen ions. Now, sometimes in exams, you might see this generalized in the terms of HA, A-, and hydrogen ions. HA is symbolic of a weak acid. Examiners do this to put you off, but please do not get put off by that. HA is literally just a weak acid, so when you see it, think of weak acids. Next up, what is the acid dissociation constant? The acid dissociation constant, otherwise known as Ka, is a quantitative measurement of a strength of acid in a solution. We know weak acids partially dissociate, but what we can do is get a value for these weak acids and actually compare them to each other to see which acid or which weak acid is the strongest. Now, again, I have my little weak acid chemical equation. Now, if I was to write a K expression, it's very similar to how you write a Kc expression from year 12. It's your concentration of your products all divided by your concentration of your reactants. In my case, I only have a reactant. So all you have to do in my case is do your hydrogen ion concentration times your A- concentration all over your HA concentration. And what does K actually mean? If you have a larger Ka value, there's more dissociation going on and therefore a stronger acid. If you have a lower Ka value, that means there's less dissociation going on and therefore it's a weaker acid. Another really important concept to start to understand is this one right here. If I had 100 molecules of ethanoic acid and only 20 of them split, which makes sense since it's a weak acid and they partially dissociate, I'd have 80 molecules left over. But out of the 20 that did split, that would lead me to get 20 ethanoate ions and 20 hydrogen ions. Notice how both values are the same and have a 1-to-1 ratio. They will have equal concentrations. Now this rule applies to most questions except for scenarios where buffers are involved. If there's buffers are involved, then you cannot apply this concept at all. If you don't seem to understand that kind of concept, let's look at pens. So if you had 100 pens and I separated 20 of them, you'd be left with 80 unseparated pens. But out of the 20 that did split, you'd get 20 lids and 20 of just the pens. And again, both values are the same. They have a 1-to-1 ratio, and that can be applied to ethanoic acid as well. Now, it doesn't have to be 20. It can be 40 that are splitting. It could be 60 that are splitting. It doesn't really matter, but the most important thing to take away is that they have a 1-to-1 ratio and they have equal concentrations in your calculations. Now you can also see in a Rice table format, which are really important because when you do start to do buffers, you'll be using Rice tables quite a lot. So at the start, I have 100 molecules of ethanoic acid, and obviously at the start you won't have any products. If I lost 20 that did split, I'd get 20 ethanoate ions and 20 hydrogen ions to add on to the initial, leading me to have 80 molecules at the end of ethanoic acid, 20 molecules of ethanoate ions, and 20 molecules of hydrogen ions. Now, please do remember the little p in pH means minus log. So, and that's minus log 10. So, sometimes when you are given Ka values, you could be just given just the pure Ka value. But sometimes the examiners and the exams can be quite mean and they can give you something known as pK values instead. Remember, the little p means minus log. So if you have pKa, all that means is minus log 10 of Ka. It's quite mean for them to do that, but it has happened before. And if you need to revert it back to Ka, all you have to do is the inverse function. And that's 10 to the power of minus pKa. Very similar to how you would do the inverse function to find the hydrogen ion concentration when you got the pH, which was 10 to the minus of the pH. And what's different is if you have a larger pKa value, that means there's less dissociation and therefore a weaker acid. And a lower pKa value means a stronger acid, stronger dissociation, and therefore it's a stronger acid. So if you look at the bottom, I have acid 1, which has a pKa value of 1, and acid 2, which has a pKa value of 2. Notice how the bottom one, acid 2, has a larger pKa value. Now, if I revert them to Ka values using the inverse function, I actually got a smaller Ka value, whereas the Ka value above for acid 1 was much bigger. Remember, bigger Ka values means more dissociation, and therefore a stronger acid. This just emphasized, this little example, why that's the case. If you have a lower pKa value, you'll get a higher Ka value, meaning it's a stronger acid. So the numbers work, and the numbers work like this just because of the use of logs. So if you're a maths person and enjoyed the understanding behind it, that's the reason to why. Now, let's have a go at some questions. Write a K expression for ethanoic acid. So first of all, let's start off with the chemical equation. So ethanoic acid, reversible symbol, splits into ethanoic ions, which look like this, and hydrogen ions. Now we're going to do as if we're doing a Kc, which is the concentration of ethanoic ions times the hydrogen ions all over my Ha, which is ethanoic acid. And that would be my expression for Ka. Calculate the pH of a solution of 0.01 mol dm cubed ethanoic acid when pK is 1.9 times 10 to the minus 5. Now, I'm going to just use my Ka from before. Now, I have my Ka value. I have my ethanoic acid concentration as well. So let's put those in. But what I don't have is the two values corresponding at the top. And that's the ethanoic ion concentration and the hydrogen ion concentration. So we've got to use that concept that we learned just a couple minutes ago. The ethanoic ion concentration and the hydrogen ion concentration are the same, excluding situations with buffers. So what I can do, since they're the same, is actually replace the ethanoic ion concentration here with the hydrogen ion concentration because they're the same. So that would lead me to do this. The hydrogen ion concentration squared all over 0.01. Now, you might be asking, why didn't I replace this one with the ethanoic ion concentration? So it turned out to be something looking like this. The reason why we don't do that is because we are trying to find the pH. pH is minus log 10 of hydrogen ion concentration. It serves us no benefit finding this out, but finding the hydrogen ion concentration does serve a benefit because then we can plug it into this equation and then find the pH as the question is asking us. That's the reason to why we don't actually replace the ethanoic ions with the hydrogen ion concentration instead. So let's continue on from this question. Let's times 0.01 on both sides. So I'm just going to do that on my calculator. That's 1.9 times 10 to the minus 5 times 0.01. That's going to give me 1.9 times 10 to the minus 7. And that's hydrogen ion concentration squared. Doing the inverse of squared is square root. So square root both sides. And that's 4.358 ... times 10 to the minus 4. I'm not going to write the whole thing, but please make sure you keep the exact value in your calculator. Now, what I'm going to do now is use the pH function, which is minus log 10 of hydrogen ions, which we learned at the very start of these acid basis lessons, is just plug that value into the formula. Again, I'm putting the exact value in my calculator, not the rounded off version. So minus log 10 of my answer, and that gives me a pH of 3.3606 to 2 decimal places. That's 3.36. Perfect. That's done. Let's have a look at this next one. Calculate the concentration of ethanoic acid when pK is 4.9 and the pH of the solution is measured to be 4.64. Now, I'm going to, again, duplicate the equation for my last question. So in this scenario, we don't have a Ka value, we don't have an ethanoic acid concentration, neither do we have anything at the top. But what we can do is actually figure out the Ka value. We can figure out the hydrogen ion concentration as well. So all you have to do is use the inverse functions. So remember, the inverse function of pK was 10 to the minus pK, and that will give us our Ka value. So 10 to the minus 4.9 is actually my Ka value. Now I can put this on my calculator and I can get it in standard form, but it's going to give me something nasty. So I'm just going to keep it like this. And the pH of the solution is meant to be 4.64. Well, we know the pH is minus log 10 of my hydrogen ion concentration. But the inverse function of that is 10 to the minus pH. And that will give me my concentration of hydrogen ions. Now, putting that value in will give me 10 to the minus 4.64. And that's my concentration of hydrogen ions. Now we can start filling stuff in. So I've got 10 to the minus 4.9 here. I still don't really know what this is. But remember, I don't still have my ethanoic ion concentration. So what I can do here is, again, using that same rule, because no buffers are involved, we can use this exact same rule what we had before. The ethanoic ion concentration is equal to my hydrogen ion concentration. But remember, we replaced them both and they turned into the squared. Hydrogen ion concentration squared. So 10 to the minus 4.9 is equal to 10 to the minus 4.64 squared all over my concentration of ethanoic acid, which I'm trying to figure out. Now I'm going to remove this space. Now times both sides by the variable that we don't know, which is the ethanoic acid. That's going to give me this, 10 to the minus 4.9 times my ethanoic acid concentration. And then divide both sides by 10 to the minus 4.9, because I want all the numbers on one side and my unknown variable on the other. Here you go. And now I can place it all into my calculator to get a nice clean value. 10 to the minus 4.64 squared divided by 10 to the minus 4.9. Don't forget the minuses, it's very easy to make that slip up. And I'm going to get my ethanoic acid concentration to be 4.168 ... times 10 to the minus 5. But I'm going to round it to three significant figures, 4.17, times 10 to the minus 5. Perfect. Let's have a look at some row exam questions. So, give the expression for the acid dissociation constant, Ka, for propanoic acid, and they've given us the structural formula of propanoic acid here. So, so to do this one, again, start off with a little expression, if you're not used to it already. It partially dissociates into the, not ethanoate, it's propanoate this time. So don't get tricked by that, like I did. And doing the Ka will give me the ethanoate concentration times my hydrogen ion concentration all over the propanoic acid concentration. Remember your products over your reactants in concentrations. So calculate the pH of 0.1 propanoic acid solution. Give your answer to 2 decimal places. For propanoic acid, pK is 4.87. So again, I'm just going to duplicate this. That's my Ka. But other things we do know, we have our propanoic acid. And that's about it. That's all the values we have. So I'm just going to insert that straight away. I can figure out my Ka though. So to figure out my Ka, all I have to do is the inverse function, which is 10 to the minus pK. And that's 10 to the minus 4.87. and that will give me my Ka value. Perfect. And we can use that same concept we did earlier, where we did the hydrogen ion concentration squared, and again that comes back to this rule, where both of them are equal. So I can put hydrogen ion concentration squared at the top. Times in both sides by 0.1. That will give me 10.47 on my calculator, times by 0.1, and I'm getting 1.34896 ... times 10 to the minus 6 hydrogen ion concentration squared. Now do the inverse of hydrogen ion squared, which is square root, so square root both sides, and I get 1.16 times 10 to the minus 3, and that's my hydrogen ion concentration. Now remember, we need to figure out the pH, so our last step is to put pH equals minus log 10 and put it into that function. I'm just going to put answer, so minus log 10 on my answer. It's actually a really clean number if you get the exact values in. So I got a pH of 2.935, but remember they wanted it to 2 decimal places, and they will always require you to do it in 2 decimal places, so that's 2.94 to 2 decimal places. Perfect. Let's have a look at the mark scheme from A-Level Chemistry Paper 1 2023, the ethanoic ion concentration times the hydrogen ion concentration all over the propanoic acid. I have the 1.35 times 10 to the minus 5. That was my Ka value. I've simplified it, and I got 2.94. Perfect. This question is about acid and bases. Calculate the pH of 0.15 mole dm cubed of ethanoic acid at 25 degrees Celsius. Give your answer to 2 decimal places. For ethanoic acid, K is 1.74 times 10 to the minus 5. So again, let's do the same thing. So ethanoic acid COO minus plus hydrogen. Now to do a K for this, it would be your ethanoic ion concentration times my hydrogen ion concentration all over my ethanoic acid. And I have my Ka value quite nicely. I have my concentration of ethanoic acid, 0.15. What I don't have are these two, but I can replace them with H plus squared. Now times both sides by 0.15. So 1.74 times 10 to the minus 5 times by 0.15. That's going to give me 2.61 times 10 to the minus 6. And that's my hydrogen ion concentration squared, just like before, square root both sides, and that's going to give me 1.61 ... times 10 to the minus 3. Now again, put that into the pH function, which is minus log 10 of the concentration of hydrogen ions, and that will give me an answer of 2.791 ... to 2 decimal places. Perfect, that's what they've asked for. 2.79 to 2 dp. Perfect, let's have a look at the mark scheme. A-Level Chemistry Paper 1 2022, and 2.79 is the correct answer. Perfect.